Hello, BNS 210. Are you guys ready to talk about effect size? Because I am. I'm chilling with Doc Brown, and Marty today as I bring you our second to last lecture. All right, so here we go. So today we're going to talk about effect size specifically. I've already posted up these PowerPoints on the Moodle, so maybe you've already looked at these a little bit. But I start off, and normally I ask the class when we do this in person, this question. And I remind you all that what we've talked about so far is statistical significance, right? We've talked about the p-value. And the answer to this question is D, none of the above, because effect size is going to tell us how big of an effect something is, but our p-value, our significance, only tells us that we have a specific percentage of committing a type 1 error. That's all it does. So if we have a 0.01, it's just telling us we have a 1% chance that when we reject the null hypothesis that we're going to be incorrectly rejecting it. There's only a 1% chance that we're wrong. If we have a 0.05, that means we have a 5% chance that we're wrong. 0.036, we have a 3.6% chance that we're wrong, and all of that stuff. So this is it. This is all the p-value tells us. It's our risk of committing a type 1 error. So if we have a p-value that's 0.46, then we have a 46% chance of committing a type 1 error if we reject the null hypothesis. So about half the time, we're going to be wrong. So that's the only thing the p tells us. That's it. That's all it's telling us. So the other thing to think about is that we've set this level at 5%, right? 0.05 is what we've set our alpha level at. And so there's not really anything to say that something is more significant than the other is kind of incorrect. We just have a less chance that we're rejecting our null hypothesis incorrectly. It's really all it's saying. Okay, so we've talked about all these things that affect statistical significance, which is of course our variability, because all of these things are worked into this calculation. Our sample size, smaller samples are going to have greater variability than larger samples. And whenever we have more people, we're more likely to see differences due to our manipulation. So our question is this real? Is what we're seeing real? How much of this difference between our groups, how much difference between our levels are actually due to our manipulation? Because that's what we want. We want our experiment to be due to our manipulation and not because of error, not because of random chance, not because of any of these other things, right? Not because of confounds. We want it to be because of our manipulation. So effect size is going to help us with that. So if you think about standard deviation to the mean and how standard deviation just gives us more information about the mean, effect size really is like that. Effect size gives us more information about our alpha. It gives us more information about our p-value. So I'm going to talk about two different measurements of effect size. And again, this tells us just how much effect any variable has. So how much effect, how much in our model did our manipulation have a role? And it's considering the random error. So it looks at variability. This calculation looks at variability. It looks at our sample size. Like all of this is dependent on our effect size. So, it's not affected by our sample size. So this will tell us what it is, what our effect is, regardless of how large or small our sample is. We can think about it like this. If we have a large effect, so let's go back. Let's use this with an example. So here I have our GPA and psychological disorder example. We did this a long time ago, where if somebody has a psychological disorder, we predict that they're going to have a lower GPA. So if we have something like this, right, where our control group got a 2.6 average on their GPA, we just took them in, we said, do you have a psychological disorder? They said, no. And we said, what's your GPA? On average, they got a 2.6. Well, we brought in people that had a diagnosed psychological disorder. They said their GPA was on average 1.2. So then we work our t-test, right? And we determine how different these groups are. The idea with effect size is if it has a large effect, that means that if we go out in the population, that this is going to be true most of the time. So with our disordered group, most people, if it's a large effect, it's going to be more prevalent out in society. It's going to be more prevalent in the population. So here we're going to have a general idea that 0.2 is our small effect, 0.5 is a medium effect, and 0.8 is a large effect. So when we're dealing with a t-test, effect size for a 2-level design does mean something a little bit different than when we deal with factorial ANOVA. So for right now, we're going to talk about the effect size and what it means for a 2-level design, for something that you would run a t-test on, a single factor 2-level design. So what this is saying is that if you have significant results and you have a small effect of, say, 0.2, what this means is that this is going to be true in about 20% of the population. About 20% of people who have a disorder are going to have a lower GPA than average. If you have a 0.5, then it's going to affect about 50% of the population who have a psychological disorder. And if you have a large effect, then 80% of those who have a psychological disorder are likely to have a lower GPA than the population. So when we're measuring effect size with a single factor 2-level design, so this is only for t-tests, this equation is known as Cohen's d. And remember when I told you guys a long time ago, you won't have to do any calculations. SPSS does it all for you, but there is one that it doesn't do. This is the one that it doesn't do. It doesn't do Cohen's d, okay? And it looks at the standardized difference between 2 means. So it considers the standard deviation of each of your means. So you actually have to calculate it yourself for this one. SD pooled is just adding both of your standard deviations for each mean. So that's what that means. So when we're looking at Cohen's d, what this means, I think I've already said this, but I just want to be clear, that if your effect size is, say, 0.65, that means that 65% of people that have a psychological disorder, on average, are going to have a lower GPA than the control. Okay, so if you want to see what this looks like on a graph, having small effects, you're going to have more overlap. So this makes sense, right? You're not going to have as much difference between your levels as you would with a larger effect. Okay, so that's Cohen's d, measure of effect size for single factor 2-level designs. So let's get into factorial ANOVAs. This is when we're dealing with your main effects and your interactions. So we're going to deal with our most simple 2-factor design. So we have a main effect for factor A, we have a main effect for factor B, and then we're going to have our interaction. Okay, so we are going to have a separate equation for each of these. Okay, so remember, this is how we've already gone over these equations and how this works for figuring out, this out, right? Okay, now, remember when we're dealing with our sources of variability, okay, that I'm just going to go through this quickly because, again, you don't need to really spend that much time thinking about this particular thing, but we have error, and you got to always consider error. And error is a huge source of variability. And again, our goal is to make sure that the differences that we're seeing is because of our manipulation. So let's go back to our idea of sums of squares. And we have our sums of squares for, that's what SS is standing for, our sums of squares, which is the variability in factor A, factor B, and then our interaction, okay? And we add all of these together, including our sums of squares error, or our within error, to get our sums of squares total. Remember that our sums of squares between is split up between all of these different things. So all 3 of these, both independent variables and the interaction, are contributing to the variability, and they are parsing out the variability. So if you think about a one-way ANOVA, when we only have one independent variable, that one independent variable represents half of this pie. It represents the entire numerator of the equation, where we have just this over the error. But when it comes to a factorial ANOVA, and this can be even more split up if you have even more factors and more interactions, right? So here we have, remember that our sums of squares between is split up and divided between all of these different things. All of this is over the error term. So it can be, so it is all portions of the same half of the pie. But now we're splitting up the variability between these different factors and the interaction. So for effect size, when it comes to factorial ANOVAs, this is represented by eta squared, okay? And so we have our variability and our error, and it's over total variability, okay? So in this equation, when we have our effect size, you have to check it in SPSS, and it'll give you that eta squared. And it'll call it partial eta squared, but it's really eta squared. I've done the calculations. It's the real thing. So if you have, say, your main effect, it has a 0.25. What that means is that in your whole model, that factor has about 25% of that total variability is due to that particular factor. So maybe it's better if I explain it this way. So here we're looking at, we have diet and exercise in this particular example, okay? So we're gonna check the estimates of effect size. Don't worry about this. I don't know why this is checked on here. I couldn't find another example. Okay, so here we have diet and exercise. Okay, so in this particular example, we have people that are trying to lose weight, and so they run this experiment, and they have people on a diet, and they have people on exercise, and then you want to see if there's a difference between diet and exercise or what's going on. Okay, so we look at the effect size. We see that diet and exercise, main effects, we have a main effect of diet, it's significant. We have a main effect of exercise, it's significant. But we do not have an interaction between diet and exercise. So when we look at this and we see the partial eta squared, what we have is 0.198. So that's about 20%. Then here we have 0.506, which is basically 51%. And then for the interaction, we have 0.02, so 2%. So what this is telling us is in our whole model, okay, so we could look at this in our model, 72, if we added it up, 72% of the variability in our entire model is because of our manipulations. But about 20% of our variability is due to diet, 50% is due to exercise, and only 2% is due to the interaction between the two. So what that's saying is that exercise in this model was more important for losing weight than diet. That exercise accounted for 50%. So if everybody in the world, right, was to do this, then that would mean that we would see, if everyone was to exercise, we'd see 50% of them would lose weight. If we did, if everyone had a diet, then about 20% of them would lose weight. So here's just a review of what the equations are for each of these effect sizes. Cohen's d, again, only for the t-test, and eta squared, which is for our ANOVA. So the Cohen's d is our statistic for a t-test for between two means. And this is saying in our Cohen's d, and this is how you write it, d squared would say that our average data point in our experimental group is that percentage different from the average data point in the control group. And then for eta squared, we're saying that whatever our eta is that that contributes to that percentage of the variability in our design. Here's how we report it in APA. I know this is what you guys want to do. You want to know about the APA format. So here's the T. Because we only have one thing, we only have 1 degrees of freedom here. And then that'll equal whatever our T is. Then we have our significance level, comma, and then our effect size measurement. So Cohen's D. And then for eta squared, we have our F, and then our degrees of freedom for whatever it is we're looking at, whether it's factor A, factor B, our interaction over our error degrees of freedom. This is our comma, our error degrees of freedom equals whatever the F is. And then again, our significance level, and then our eta squared following it. So that's it. That's all I have to say about effect size. Thank you once again for watching, and stay tuned because I'm going to record power and confidence intervals next. Thank you.